So good morning everybody. We start with a very interesting theorem which played a prominent role in mathematics or continue to do so. Because you would have all heard about what are called fixed point theorems. And fixed point theorems play a very important role in proving the existence of solutions of certain equations. I will demonstrate this point. Then after that we will see what exactly is a fixed point theorem, and then we will see what are called the contraction mapping principles. Okay. So let us consider the following problem. Let I be an interval. A closed interval. Closed bounded interval. Now, let us look at a map from F from I to I. So I is of the form, I will take it as something like 0, 1 for instance. Specifically I equal to 0, 1. Now let me look at the map F from I to I, from 0, 1 to 0, 1. So for each x belonging to 0, 1 implies f of x belongs to 0, 1. We also assume f is continuous. Like a polynomial. Now the question that you ask is the following. Does there exist a point x belonging to 0, 1 such that f of x equal to, this is the question. Does there exist a point x belonging to the interval 0, 1 such that fx equal to x? If there exists such a point, then you call it the fixed point of, or a fixed point of fx. Now geometrically the problem is this. Now you know that you go to the graph of the function. Consider this square. You see that this is the function y equal to x. Now you have the graph of y equal to. So this is y equal to f of x. Now f is a mapping from the interval 0, 1 to 0, 1. So an arbitrary point on this graph is designated by x. So that's the graph of the function. Yeah. Now the question that you are asking is this geometrically. Do you have points on this interval such that, on the interval 0, 1 such that fx equal to see, these are the points. Suppose you call this x1, x2, x3, then you see that f of xi, xi from the graph it is clear that this point is xi, fxi. Then you have this point is xi. This point is x1, x1. This point is x2, x2. This point is x3, x3. So these are the 3 points that you have for the in the particular picture or problem, which are the fixed points of f. Now that is the graphical representation of that. Now let us see, I have not assumed anything here, that I have not even said that f is a continuous function. Okay, so let us consider the same problem. Let's consider a discontinuous function. A discontinuous function, I take a discontinuous function which is something like this. Whose graph is this? That means there is some point, say, if you want to be specific, you can say half, where the function is continuous on the interval 0 to half, and the function is also continuous on the interval half to 1, but has a discontinuity at half. Now what happens to this function? Does it have any fixed point? Because you see that the graph never crosses this particular line. If it crosses the line at a particular point, then you see that it corresponds to certain fixed point, and it doesn't happen. So in this case, there is no and in this case, there are fixed points. Essentially, you are solving an equation of the form x is equal to the form. You are asking whether this particular equation has a solution or not. Okay, so it's an equation. F(x) equal to x is an equation, and you are asking the question: does there exist a the solution to this problem on the interval 0 to 1? Okay, we have seen two scenarios. One, there is a continuous function, and one, there is a discontinuous function. In the case of discontinuous function, we have seen that there is no fixed point. In the case of discontinuous function, there is a fixed point. That means there is a solution for this particular equation. So this is something that you bear in mind. Therefore, one can, at the outset itself, one can say that if you are looking for a general result, what conditions on f will tell you that there exists a fixed point? You can certainly say that if the function is discontinuous, in general, there is no fixed point. I am using the word in general. So that means there are discontinuous functions for which there is no fixed point. But it appears the mapping is from the interval 0 to 1 to 0, 1, and if you have a continuous function, there are fixed points. Now this is a question, so you can ask the question: if you have a continuous function, do you have a fixed point? And at least this example shows you that there may be fixed points, but there may be far too many fixed points, because it depends on how much the function would oscillate. Now this is the question that you have. Okay, that is one case. So one of the scenarios in which this result, if you could prove, if you could get a general result, now that could be used is in establishing the existence of solutions of an equation. Now, I just tell you that the problem is quite involved. In fact, even for polynomials, suppose P is a polynomial. Suppose you look at this equation. So, Px equal to 0. So, you assume that the polynomial is of degree n is say 10 or 15 or something like that, a big number. Is it possible to find the zeros of this polynomial? In general, there is no general method to do that. Maybe if the degree of the polynomial is 1, it is easy. If the degree of the polynomial is 2, then it is easy. Then the degree of polynomial is 3, then also it is possible, possibly. And then, you know, it is 4, you can do it, but from 5 onwards, you cannot give a very general method for finding out the roots of this polynomial. So this problem is finding the roots of the polynomial. However, you have very nice theorems that if the associated field is C, then this polynomial has all its roots in C. It's an existence theorem. You are not saying that this point is the root of this polynomial. If the degree of the polynomial is n, then it says that there are exactly n roots for this problem in C. So there exists fundamental theorem of algebra. But it also does not give you a method of actually computing the roots exactly. You don't have a method. You can probably approximate. There are some methods through which you get an approximation of that, but no general method is available to find the roots of this. If by chance you see that one of the roots is lambda 1, then you can filter out lambda minus lambda 1 from this polynomial and get a lower degree polynomial, and then see whether you can have a solution of that node. So once the roots are known, suppose some of them may be repeated roots, lambda n are the roots, then you have got Px written as some in C. But if you ask the same question in R, it is not it's not possible to make this statement. For instance, if you take x square plus 1 equal to 0 and search for the roots in R, then you see that there are no roots at all, because both the roots are I and minus I. I don't want to digress in that direction. But can you pose this problem as a fixed point problem? This is the question. So we have got this equation Px equal to 0. We want to find the roots of this equation. What I do is, I'll write Qx. I'll define Qx to be equal to Px plus x. Okay, that's the new function that I am introducing. Now you see that lambda is a 0 of P if and only if we have P lambda plus lambda equal to lambda. What does this mean? That is, if and only if it is a fixed point of qx of q of the polynomial q. Q is also a polynomial, or it is a root of the equation This is the meaning. Therefore, any problem of this kind, that is fx equal to 0, that is finding the zeros of a function, can be redrafted as finding the fixed point of a different function. That is, all that you need to write is define gx plus x, and then roots of or the zeros of the function f are essentially the fixed points of G. So we have converted the problem of finding the roots of a function into finding the fixed point of a different function. We have not solved the problem. That is the important point. We have not solved the problem yet. But we have converted it into a new problem. So how to find the fixed point? That's the problem. Now let us generalize this. Now I will not, because it would take some time to develop the necessary machinery, but I will just tell you another scenario where the same problem would occur. Okay. I hope you are all familiar with what are called initial value problem in the context of differential equation. So let us consider the following differential equation. Y derivative is equal to f of xy, where f is a given function which is assumed to be smooth in both the variables, etc. and so on. Okay. Now, you know that under certain circumstances, this equation has a unique solution satisfying the condition yx naught is equal to y naught. On an interval containing x naught under certain circumstances. Yeah.
So we are not able to see the screen, sir.
You are not able to see this?
Screen at the bottom.
Okay, I will switch over to another this one. I think there is something they are saying Airtel pack is expiring. Okay, it doesn't matter, right? Yeah. Are you able to see it now?
Yeah.
Some message came, that is the reason. Okay, so this equation has a unique solution on an interval containing x naught under certain circumstances, certain conditions. Now the problem is how to establish this. It's a general theorem. F is satisfying certain general conditions like continuity, and then you are asking whether this initial value problem has a solution. You all recall this is approached by converting this problem into an integral equation, because you can see that formally this can be or even written as now you see that if you look at this integral equation, all that I am doing is this. I am assuming yx is a solution. Then I have y derivative of x is equal to f of x yx. What I am doing is I am just integrating. If I integrate on both sides from x naught to x, what I get would be yx minus yx naught equal to integral x naught to x f t yt dt. Conversely, suppose this equation is given, then by differentiating both sides you get y derivative of x is equal to f of x yx. So these two, therefore one could show that finding the solution of this initial value problem is equivalent to finding the solution of the associated integral equation. Therefore the problem is now solved. Does there exist a solution? For 2. If you can show that the second equation has a solution, then that defines a solution for the first problem. Now if you carefully look at this, now I take this part, and formally I can write it this way. I write this as, let me define, t of y I define as y naught plus x naught to this is exactly the Picard's approximation method that you are trying to do, right? This is the definition of t. Therefore, what t does, t acts on a class of functions which are differentiable and convert it into another function. So t f of or t of y from zx, where zx is given by this expression. Or in other words, what you have is you have an equation, zx is equal to t dx. Now the problem is, what you see here is, if y is a continuous function on some interval, then it defines, t of yx defines another continuous function on the same interval. Okay, we choose an interval which contains 0. Sorry, x naught. Okay. Therefore, this acts on, functions on some interval a, CAB, with x naught belonging to AB. Okay. So this is what you have. Therefore, the question is, a fixed point see, T is considered as a map from CAB to CAB. T is a map from for some interval AB. You are asking whether T has a fixed point. That means, does there exist a a function y of x defined on the interval AB which is continuous such that T of y equal to T of T of y equal to y. That solves this problem. So this problem has been now converted into another problem asking for a fixed point of certain mapping. Okay. So you see that there is a lot of similarity between what we did earlier for polynomials or even continuous functions and this problem. So in diverse environments or circumstances, in diverse problems, you see that the same question is getting asked. So how to handle this? Now this is the problem. Now let me abstractly formulate this. We take T as a map from, okay, let X be a metric space. That means X is a non-empty set with a notion of distance defined on that. So what you have is X rho. I presume that all of you know what a metric is. In this case, CAB is a metric space with the metric defined as the distance between two functions, and two functions y1 and y2, the distance between the two functions is defined as d supremum of over x belonging to AB of mod y1x minus, you can show that this gives a metric or this gives a notion of distance between two functions. It is nothing but this. You have an interval AB. If you have two functions, this is y1 and this is y2. So this is y1, this is y2. Then what you are looking at is the distance between these two functions at every point. You are measuring. So for a particular x, this distance is what you call y1x or y2x minus y1x. Take the absolute value of all those distances and look whether the supremum exists or not, and if the supremum exists, that you call the distance between the two functions y1 and y2, and you know that if the supremum is 0, then you see that the two functions become identical. because I am taking continuous functions. Okay, right. So that is just about the metric that you have. Now we take a map T from. So T is a map from the metric space X into the metric space X. Now the fixed point problem is the following, or the abstract formulation of all these problems is the same, is given by this. Does there exist a Z belonging to X such that that's about the existence part. That means the point Z is back to itself. Okay, I'll make it more clear with an example. Now the second question is, if it does, is this unique? That's the second question. Okay, you know that for all T this is not going to be true. That means that you will have to put certain restrictions on your T, the map T. Okay, let us consider a nice example. Now you would have seen the frame that you use to hold the cloth straight. Okay, so a frame like this, you have two rings like this, and one that goes inside the other one with some kind of a screw mechanism to tighten it and so on, which most of you will be using. So what you do is, if you want to stitch, for instance, you want to do some kind of a nice stitch, a sort of flower on the cloth, what you do is you put this cloth inside this frame, stretch it and keep it there and tighten it. Then you are comfortable in stitching it. You make a picture of your flower and then start using your stitching it. So that's what you do. Okay. Right. Now what happens? What I am going to do is take this frame, and on this frame you take a rubber sheet and clamp it. You stretch the rubber sheet in all directions. Okay? You stretch the rubber sheet in all directions and then clamp it. What you have is the rubber sheet fills this region. Now what one does is, then what you do is, see, you mark the boundary of the sheet that is there inside this frame. That is possible. Okay. After that, what you do? You release it. You unscrew the whole thing and release it. What will happen? See, this particular marking that you have done, it will take a form like this. This is the interesting part. The marked portion will contract to a region like this. What has happened? So what has happened is that the points that earlier were inside this ring, or inside on the sheet inside this ring, has now moved inside. So you have got points moving inside like this. Okay, from all sides it has happened. So essentially you can look upon this as a mapping. So if I call this your x, and then you see that there is a map x from P from x into x. That is this particular map that I have defined. So if you consider this as x, then this point is Tx. Points here would have moved somewhere. So you see that there is a redistribution of points all over. Okay, am I right? You can easily find out the path of a particular point. If you in the original stretched frame, you mark a point and then see where it reaches after you de-stretch it. Okay, so you will get something like this. Now the question that you ask is, it's not at all clear here. Does there exist a point in x which has not changed its position? In this abstract problem, it is clear. Why should there be? You don't know. But you will be happy if there is one. And you will be all the more happy if there is exactly one. So that's the question that you are asking. Does there exist a point in this x which has not changed its position? Such a point is called a fixed point. Fixed point. So let me just briefly repeat what I have done. See, I have taken a frame, put a stretched membrane inside that, a rubber sheet or something, and then what I did was I released the whole thing, or before that I marked the outer boundary, then released it, then you have this outer boundary going over to this boundary. So every point inside this particular portion is now moving inside this particular portion. So that can be considered as a mapping from x into x. I designate it by t. Now the question I am asking is, does there exist a point in x which has not changed its position? It's not very clear at all that there would be such a point. Okay, such a point is called a fixed point. Now in this problem, what you can prove mathematically is that there exists exactly one point in x, say y, or say z, such that tz equal to z. It's a very strong statement. First of all, there exists a point z. The second part is exactly one point having this property, and this is what's called the fixed point theorem is all about. Okay, you can consider this particular x as a metric space because you have it's in R2 and you know the usual distance, notion of distance between 2 points in R2 is there. That will serve as the metric, and with respect to that metric you are talking about a contraction, and then you are asking whether t, if t is a contraction, then there would be some fixed point in this case. And what you are saying is that there is what you are going to prove rather is that there is exactly one set in X such that T set is equal to set. This is the fixed point theorem. Okay, now let me more carefully formulate it and then possibly suggest a proof of this. So X is a complete metric space. So I have put one more condition that it's a complete metric space. Secondly, T is a map from X into X. T is a map from X into X. Assume T is a contraction. What do you mean by that? This means the following. The distance between Tx and Ty is less than or equal to alpha times distance between X and Y. That means if you start with 2 points here, say X and Y, there is a distance between them. Look at their images under the map. That is the distance between Tx and Ty. What it says is that the distance between X and Y, Tx and Ty is less than or equal to alpha times d of xy, where you put alpha lies between 0 and 1. Then T is a contraction. Then T is a contraction map. So under this condition, this is what you call a contraction map. That means 2 points have been brought closer by the map T. This is the meaning of that. Then there exists exactly one point such that this is the contraction. This is the fixed point theorem. This is what's called the Brouwer's fixed point theorem. It's a beautiful abstraction of a very concrete problem that you encounter. And you know that fixed point theorems of various types have been proved since then, and they are used very extensively in in establishing whether there exists unique solutions for a given differential equation in the context of the study of partial differential equations and ordinary differential equations. That's about the application part. Now, let me see how you prove this. The proof of this is not very difficult. You do a very natural thing. You are all familiar with what is called the Picard's approximation. What do you do for Picard's approximation? What you do is you start with a function, some function, and then put it inside that integral, and then compute a function. So you start with some y0, then compute y1, then compute y2, and so on. Then you compute a sequence of functions, right? And under some conditions on the differential equation, you prove that this particular map is a contraction map, or the sequence of functions yn converges to a point, and then you assert that that point is a fixed point. Okay, let us see that. So we start with let z0 belong to x. What you do is you define T of Z0. And then you define Z2 as T of Z1. And so on. You define Zn as minus 1. And so on. So what you produce is a sequence of functions or a sequence of points Zn containing particular x. Pictorially is this. Suppose this is your metric space X with all those conditions. Now what you do is you start with a certain Z0, map it with the T, get Z1, map it with T, again you get Z2, map it with T, you will get Z3, and so on. And so on. So what you get is a sequence of points in X. Now what you assert is that if T is a contraction, then T has a fixed point. Okay, what is the logic that you follow? This is what you have. So you have now got a sequence of points Zn with the property that Zn equal to T Zn minus 1. Right. So I can write Zn equal to T Zn minus 1. Let me let n tend to infinity. Suppose the sequence converges to some z. This is equal to z. What about T Zn? You are taking this limit of n tending to infinity of T Z n minus 1. And this is the question that you have. If this is possible, if this is limit n tending to infinity of T of, if it is T of Zn minus 1, then this is equal to T of Z. Therefore, what you are looking for is the limit of the sequence Zn. Formally, if you can justify all these steps. Okay? If you can justify all these steps, then Z is the limit of Zn. That is the fixed point that you have. So let me do that. Okay, let us see, the strategy is this. Show that under the contraction assumption, Zn is a Cauchy sequence. Now it is everything is clear, because once you prove that this is a Cauchy sequence, then you know that you are working in a complete metric space, and in the complete metric spaces, so in a complete metric space, all Cauchy sequences converge. and of course the limit is unique. Okay, right? So the problem is solved the moment you show that Zn is a Cauchy sequence. Now what you do, what you want to say is this. D of given epsilon, there exists given epsilon, there exists an n which depends on epsilon such that d of Zm Zn is less than epsilon. For every n m greater than n. So if you can establish this, then it follows that Zn is a Cauchy sequence. If it's a Cauchy sequence in a complete metric space, then it converges to a unique point, and that point in turn will turn out to be the fixed point of T. Now this is the strategy. So just do that. I mean, that's very easy. What is the condition that is given? It's a contraction mapping. So under the condition that the mapping T is a contraction, you get this result. So what do you have? Okay, let us start working out the. So what you have is that xn plus 1. Etc. Now we take alpha less than, therefore you have d of this is equal to d of this is less than or equal to alpha times, okay, this is equal to d of T Zn T minus 1, and that is less than or equal to alpha times I have used the contraction mapping condition over here. Alpha is less than 1. Okay. Now what I do is, you can essentially prove the following. You can link everything to the distance between Z1 and Z0. So you can show that d Zn plus 1 Zn, by repeatedly applying it, is less than or equal to Z to the power, what is it? Alpha to the power n d of now this is the crucial inequality that you have to prove, and that would follow straight away by applying this. I mean, you can, that's the only thing that you have to do. Therefore what you have, you have d of this, you can show that this is less than or equal to sigma I equal to n plus 1 to m d of xi minus 1, and that is less than or equal to, using this inequality you get alpha to the power n plus alpha to the power n plus 1 plus etc. The last term is alpha to the power n minus 1. times d of z1 z2. This is what you can do. And therefore this is equal to, this is less than or equal to 1 minus alpha to the power minus 1 d of z0 times alpha to the power n. Now this inequality immediately tells you that what I wrote, that given epsilon there exists a n epsilon such that this is less than epsilon for all m and n greater than n epsilon. From this inequality you follow. Therefore what we have proved is that and you also have t now proceed to the limit as n tends to infinity, and what you have is that, so you have, if I write z as limit zn, then we have, that's quite easy to do. Okay. So that is that is a fixed point. Now the next question is this unique? Suppose there are two fixed points, say z and z tilde are two fixed points. Then what do you have? You have tz equal to z, tz tilde equal to z tilde. Now you compute the distance between z and z tilde, or distance between tz and tz tilde. This is equal to distance between z and z tilde from this equation. But what you have is d of, since t is a contraction mapping, that's a contradiction, because the value of alpha is strictly less than 1. This is a contradiction. Okay, therefore there exists exactly, that's a contradiction. If a fixed point exists, then it is unique, provided T is a contraction. Okay, so this is the contraction mapping theorem. Now I have seen that many problems in mathematics where you search for the existence of the solutions of certain equations, you can somehow or other gear it into the language of a map on a metric space, as I have demonstrated in two scenarios where you can do it. Okay, now I'll just give an example. Take the simplest case that we have considered. So F is a mapping from and you have the distance, usual distance that you, so your metric space is the interval 0 with the usual distance d of then you know that this is the interval, then x is a complete metric space. So your problem is this: does there exist a solution for the equation fx equal to x? If the map f is a contraction, then it happens. Okay, so what you are doing is this, that is, if then what you get? So what do you require? This is what you require. You want modulus of fx minus fy to be less than or equal to alpha times mod x minus y. So this is the contraction mapping condition that you have. So you can convert this by giving a condition on f. So assume f is such that f is differentiable on 0, 1 and mod f derivative is equal to some alpha is less than or equal to alpha and alpha is less than 1. Then you have to prove that this is a contraction. How do you do that? You can use your intermediate value theorem. So what you have fx minus, not intermediate value theorem, you can use the mean value theorem. Fx minus fy is f derivative at some point psi x minus y, where psi belongs to the interval 0. Now all that you need is the condition that mod f dash less than. And for all such functions, there is a unique fixed point. Now it will take some more time for me to do, if you want me to do on the in the differential equation case. But I would suggest that I have a talk done some time back in Cochin University, exactly application of fixed point theorem to finding out the or solving the existence and uniqueness theorem for differential equations. You may go to that. So with these few words, let me take leave. Thank you very much for this wonderful opportunity to teach mathematics at your university. Thank you very much.
Thank you, sir. its structure. Hope all had a useful time with you, sir. Finally, we call A. Shastri, second UG Mathematics, to give the word of thanks. Honorable Chief Guest, Professor Vinay Krishna Kumar sir, respected dean, Dr. Mrs. K. Avinashlingam ma'am, Dean School of Physical and Computational Sciences, respected HOD, Dr. Mrs. D. Jayalakshmi ma'am, Department of Mathematics. It's my privilege to have been asked to propose the votes of thanks on this occasion. Let me call it a fraternity of young mathematicians here together, and on my own behalf, extend a very hearty vote of thanks to the speaker, Professor Vinay Krishna Kumar sir, for gracing your important work and sharing with us your findings and your opinions today. We are all inspired by your great work, sir. A big thanks to our respected dean, Dr. Mrs. K. Avinashlingam ma'am, for permitting us to conduct this fantabulous meeting. A special thanks to our HOD, Dr. Mrs. D. Jayalakshmi ma'am, and the other faculty members present here for the perfect logistics support and guidance. I cannot thank everyone enough for their involvement and their willingness to take on this meeting beyond their comfort zone. Finally, I would like to take on this opportunity to present our hearty thanks to all the participants of today's show. I would like to thank AC Nandini for designing the invitation. Without you, all this meeting would have been like a moment without a sugar. Thank you all. Sir, thank you, sir.
Okay, thank you very much. I would like to thank Shamina especially, who contacted me and gave me this opportunity. Thank you very much.
Yes, sir. Okay, sir. Thank you very much, sir, for accepting your invitation.
Yeah,
Thank you, sir.
thanks.
Okay, HOD Mathematics Department, sir.
Okay,
Jayalakshmi.
yeah.
Okay, sir.
Okay, bye. So shall I take leave or you want me to answer some questions? So shall I take leave or you want me to answer some questions?
Yes, if you have doubt, you can ask. Yes, if anyone have doubt, you can ask.
Okay. This talk, let me just make a
That's
statement.
why let have no doubt.
Okay. This I want to make a statement that this talk is recorded on the YouTube, and you can listen to that or in your leisure on the YouTube if you want, because it is always available in my channel. This is the channel is Krishna's Classroom. There are so many lectures uploaded on that. You can have a look at that. Thank you very much.
Yes, sir. Sir. Many students subscribe to the channel, sir.
Thank you. Okay, so shall I take leave then?
Okay.
Thank you very much.
Okay, sir. Okay.
Just turn it off.